Welcome everyone to this video. So, we want to begin today with a new chapter. Um, so, you might have heard about, or you might have seen, how a balloon is filled up when we basically uh, blow air in it, and how the air basically fills up the whole volume of the balloon, and it changes its state depending upon the surrounding temperature. For example, if you were to take that balloon to an area whose temperature is higher than it was previously in, then the balloon will probably shrink in size. So things like that can happen. So why do they happen? We say that because the balloon contains some air particles or whatever air we had blown in through it, uh, it actually cooled down. And upon cooling down, the molecules inside the balloon, it they slowed down. So they had a corresponding effect on different extensive properties of the balloon. By which I mean what is the pressure of the balloon, what is the volume of the balloon, and so on. Things like that. This is one of the examples which came just to my mind. So we want to basically relate that how those particles in the balloon, how fast they are moving, how do they decide the extensive or macroscopic properties of the gas inside the balloon, and how the macroscopic properties decide the motion of the individual particles at the microscopic level. So this is made possible by the theory which I'm telling, that is kinetic theory of gases. So we talk about gases uh, in the sense that they make up most of the observable universe. Um, Most of the universe is basically hydrogen and helium. So, in fact, in that balloon example, if we fill the balloon instead of uh, normal surrounding air, we fill it with helium. Then we have seen that the helium balloon are much lighter in nature. So, at the particle level, how are they distinct to normal air molecules? What actually changes when we uh, change the nature of gas? So, first we think about what are the laws which we use to define the observable behavior of a gas. So we have a theory. We say that according to that theory, if gas follows some certain laws, then its observable behavior would be somewhat uh, be predictable. That is what the law says, and what we'll observe will be having some close relation. So, one of the laws which we start with is ideal gas law. So ideal gas law says that okay, if a gas has a pressure P, has a volume V, moles of the gas are some N, universal gas constant is some R, and temperature is some T, then they are related by this relation. That is, the product of pressure and volume is equal to the product of moles of the gas, the universal gas constant, and the temperature of the gas. So as you can see, all these are macroscopic properties. Um, so if any of the gas which follows this kind of law, we say that kind of gas is called an ideal gas. So we have observed that okay, whatever gases we have available with us, they follow this law at low densities. So I just want to basically write down what does P, V, N, R, and T denote. So P denotes the pressure of the gas. So in that balloon example, what would be the pressure of the gas if I basically fill the whole balloon with some air? So volume of the gas. So how big is the balloon? Let's say we are celebrating a balloon of but not the balloon. We are celebrating a birthday of a let's say uh, a small kid who likes balloons, who likes a lot of balloons. So we'll be filling the balloons all over the place. Some balloons will have high volume, some balloons will have low volume, and most of the balloons they'll be filled by some of his parents or some of his brothers or cousins, and in the end, even friends can come up and help him out. So, what happens to the gas when the basically balloon gets burst? What happens to the volume of the gas when it bursts? It definitely expands. So, volume of the gas is an important property. Then, how much air we have filled in the balloon? That is decided by number of moles. So this number of moles is basically decides that okay, what are uh, it's approximately the number of particles, or not approximately exactly the number of particles which we have blown inside the balloon. So at first it is very you know kind of interesting thing that how we are able to exactly determine the number of particles which we have blown in the balloon or which will come bursting out of the balloon if it is popped. But we can do that. And not only we can do that, we can say that okay, the pressure and volume of the gas depend upon the number of particles for a given temperature. For example, if I have some temperature of the gas given gas temperature is T and P and V are there, pressure and volume, they or pressure of the gas is given. So if we blow more moles of gas inside the balloon, then the volume of the balloon will be more. So this is a direct, this is a uh, visible relation, right? If temperature and pressure are kept constant, so increasing moles will increase the volume. So pretty logical thing to think about, and which follows that equation as well. Then R is called the universal gas constant, and T is temperature in Kelvin. So this value of R is some 8.314 joule per mole per Kelvin. So this is an experimentally uh, calculated value. Next, we have other laws as well, which we will name, but we won't discuss as much. We'll discuss them later. Uh, so one of the laws is Ball's law. So we'll discuss till that K, the constant temperature. So when temperature of the gas is a constant, we say the gas will follow this law. And we have Charles' law. Charles' law says that pressure is constant. And then we have Guy-Lussac's law. Guy-Lussac's law says that the volume of the gas is constant, then what is the relation between pressure and temperature? Then we have Avogadro's law. Avogadro's law is that if pressure and temperature is given, then volume is proportional to moles of the gas. So this is like a famous law that at standard temperature and pressure, basically uh, 1 mole of the gas will be contained by this 22.4 liters of volume. So then the last law which we have is law of partial pressures. So that is also there. So all these laws they combine to give us that equation which we discussed. That is the ideal gas law. The first thing which we discussed. Now let us actually move on to the assumptions. Gases are pretty common in our world. They help us uh, create different kinds of uh, environments. Let's say if you are uh, at a DJ party, right? So in a DJ party, you would have seen that they have those uh, guns in which from which, or let's say they have that pyrotechnic equipment from which gases is released in atmosphere. For example, you are attending the basically you're attending some kind of wrestling match. So Kurt Angle is about to matlab, enter the stage. So they will fire that uh, you know uh, smoking guns in air so as to attract the attention of the audience that the fighter has or the wrestler has come in. So how do they matlab, think that okay, this is the speed with which we will be firing the gas? If we fire the gas at this particular speed, then how would you calculate till what height will the gas go up till in air? So pretty fascinating questions. So we need some assumptions basically, or what we say postulates of kinetic theory. Writing in short because kinetic theory because that is already written here, kinetic theory of gas. So postulates of kinetic theory. So that is what we want to discuss one by one. So mathematically, we are not delving into a lot in this video. uh, we want to basically discuss what this theory entails. So the first assumption is that the molecules or the atoms, let's in that case of helium gas, helium usually does not form molecules with itself or with other atoms. So atoms of a gas or molecules of a gas, they are very small in size in comparison to the container in which they are placed. So this is the one of the you can say assumptions of kinetic theory. You can't say this is a whether this is going to be a real thing, but we have to assume this if we want to uh, move ahead. Then now the postulate. What do word postulate mean? Postulation again means that it is some kind of assumption only, right? Under some circumstances, we are theorizing that this is going to be a true statement. So that's what I understand. And next, the uh, collisions between the molecules in air are completely elastic in nature. So this is like the second postulate that the collisions of molecules with themselves and with the wall of the container are going to be elastic. Reason being that the molecules don't themselves transfer a lot of energy to each other when they are interacting with each other, or whatever energy they transfer to the other molecule, that molecule circles that energy throughout the system. By which I mean is that if particles exchange some energy, then that energy goes out somewhere in the system. So overall, the net energy of the system remains the same, and the particle itself has not lost any energy. Then, uh, let's say we have collisions of a gas particle with the container walls. Those are also considered elastic. So we have elastic collision. We can write that elastic collisions. Then intermolecular distance are so high that particles only interact during collisions. Then particles follow Newton's laws. So that is also one statement. Then we have uh, um, the statement that basically the particles, whatever particles they have, they'll be having some, uh, let's say, velocity. So, and will have some density. So, the density of the particles won't be uniform in a gas. So, that is like a statement which means that the gas is at steady state. Then, the last statement which we have is that the distribution of the particles and their positions, their velocities are uniform throughout the uh, container. So they are uniform throughout the container at different positions and at different directions. So this means that if I have some large number of particles, so this is true for large number of particles only. If we have some particles of the order 10 to the power 19 or 10 to the power uh, 23, as in the case of Avogadro's number. So, if let's say some particles, some thousand particles are moving in this direction with a velocity 10 meter per second, then we can easily say that okay, those some other thousand particles should be moving in y direction with approximately the same speed, 10 meter per second or somewhat near that, because all the particles cannot have the same speed. So on an average, they will have that particular speed in x direction or in y direction or in any direction. Basically, if you choose somewhere between x and y also, you will find those particles. So that means that the gas is not preferential to some directions. The gas itself is uniform throughout, which is pretty logical, but it's not so. If why we mean logical in that case, this happens only in cases where we have very large number of particles. If let's say only 10 particles are there in the system, then it won't be so true. Exactly, it won't be true. So we have to make some assumptions which are definitely true in real life cases, and not true if you're talking about, let's say, if some atmosphere is there or some planet on which there is no atmosphere at all, no particles are there. There you would have seen only two, three particles are existing. So how would you judge that? What is their temperature? How would you even define temperature for such a case? So these are basically the assumptions. One of the assumptions which I would have missed is would have been that um, that the particles do not have any intermolecular forces. So that I have written here only. Intermolecular distance are high, so the particles only interact during collision. So intermolecular forces are negligible only. So these are the postulates of kinetic theory. So that's it for this lecture. Thank you.